Welcome to this video on the numerical solution of ordinary differential equations. And in this video we'll be looking at an overview and the classification of methods and the general solution approach that we would follow. So we have looked at analytical solution approaches in a prior video. But what if we can't find an analytical solution? Well, then we'll have to resort to a numerical solution of the ODE. Now, what would a numerical solution to an ODE look like? Well, we know that the analytical solution is a function. But the numerical solution will be a set of discrete points that approximate this function. Let's say y of x is the analytical solution to the ODE. Then the numerical solution would just be a set of discrete points that approximate this y of x. Now, since the solution is given only at a set of discrete points, the solution is usually only determined on a given interval of the independent variable, right? Somewhere between a lower bound a and an upper bound b. That doesn't have to be the case for an analytical solution, right? Where the independent variable could go from minus infinity to plus infinity, but if we represent the solution by discrete data points, we can't cover from minus infinity to plus infinity, so we'll restrict ourselves to a known interval from a to b with the solution points. Now, we can choose to give the solution at equally spaced points in the interval. So, for example, if we had uppercase n intervals, that would mean we have n plus 1 solution points, where the first solution point x1 would be at the left bound of the interval a, and the very last point would be of the independent variable x would be x sub n plus 1 would be equal to the right bound of the interval b. And then the solution is a set of points x1, y1, set of data pairs, y1 being the approximated value of the solution function y at x1. Then we have x2, y2, all the way to xn plus 1, yn plus 1. So let's look at a first order ODE and look at the general solution procedure. We will start at a point where the initial solution is given. Recall that we need, for a first order ODE, we need one constraint that if the independent variable is time, that would be the initial value. Okay. With that point, we use that point then to determine the solution at a nearby second point. Once we've determined that nearby second point, we'll use those solutions to determine the solution at a nearby third point. And we keep on repeating this until all solution points in our interval are calculated. Let's classify numerical methods before we dive into some examples of numerical methods. One way to classify numerical methods is whether they use a single step or multi-step. So single step means that the solution at the point xi plus 1 depends only on the solution at one prior point xi. Whereas then multi-step would mean that the solution at xi plus 1 depends on the solution, or can depend on the solution, of multiple prior points, so xi minus 1, and so on. Then we classify methods whether they are explicit or implicit. Explicit means that the solution at y sub I plus 1 depends only on already known solution values. So for example, y sub I, the solution at the prior point or points, and the values of the independent variable xi, which can be at xi or xi plus 1. An implicit method, on the other hand, means that the solution y sub I plus 1 does or can depend also on the not yet known solution yi plus 1. So it would have the following form. yi plus 1 is equal to some function of xi and xi plus 1, yi, all of these are known, but that function may also contain yi plus 1. So we're left in this case with a root finding problem. Okay, so now let's apply this procedure to solve the following first order ODE. Dependent variable is y, the independent variable is x. So the first order ODE has the following form. dy dx is equal to some right-hand side function that is a function of x and y. It's a first order ODE, so we need one constraint. And that constraint is that at x1, y is equal to y1. And the values of x1 and y1 must be given. Okay, so how do we solve this? Let's integrate both sides from the initial value x1 to an arbitrary value of the independent variable x. Okay, so we'll integrate the left-hand side here. Integral from x1 to x of dy dx dx is equal to the integral of the right-hand side. So the integral of x1 from x1 to x of f of x and y dx. Okay, on the left-hand side, if we do this integral, right, the dx is cancelled. So we have simply y at x minus y at x1 is equal to whatever we had on the right-hand side, this integral from x1 to x of f of x and y dx. So let's isolate the solution. Y of x would be equal to y at x1, but that's my y1, right, the initial constraint, then plus the integral from x1 to x of f of x and y dx. Okay, now let's apply the procedure that we've outlined above. So we start at a point where the initial solution is given. So the first point is x1 and y1, right? Because that's given by the initial constraint. Then knowing this solution x1 and y1, let's use that to determine the solution at the nearby second point, x2, y2. So in the graph here on the right, we'll start at a general xi, yi, and we want to go to the neighboring point xi plus 1, yi plus 1. And we want to do this following along the solution to the ODE y of x that's shown here as a red line. Now, how do we go for the independent variable to the neighboring point? Well, if we equally space the independent variable, then the new value x2 is just the prior value x1 plus the step size h. And y2, the new value of the dependent variable, would be y1 plus, let me just say, a slope times h. And we'll have to determine what this slope would be. Okay, so that would be, if I have some way of finding out what this slope is, that would be the solution at the second point. And now I just keep on repeating this, using this information x2, y2 to calculate the solution at the third point, and so on. So if I go to the ith point and I want to calculate the I plus first point, then xi plus 1 is xi plus h. And yi plus 1 is equal to ya plus some slope that I don't yet know times h. Now, we will cover different methods of calculating this slope. But let's see what that slope actually is from a formula point of view. So the slope, right, is the derivative dy dx, right, which is f of x and y. But what the slope really is, right, this integral, the average of the f of xy in the interval from xi to xi plus 1. It's the mean value of the slope of y of x from xi to xi plus 1. So it's this integral divided by h. That would be the analytical form of the slope. So it's the average slope. So that would be indicated here by this line. Thank you for watching.